Hello and welcome to 8.8 Improper Integrals. So here in this section we're going to be looking at areas that appear infinite but we find out that they are finite. Okay, so here we have two cases where it appears if the graph continues we have what looks like area that would be infinite, but we find out it's finite. Similar scenario here as we get closer to this vertical asymptote, we might think that we have an infinite area, but it's finite. So let's take a look. We have some definitions of improper integrals of type 1. Okay, so type 1 we have these integrals. Either one of the bounds is infinite or negative infinity, or we have both bounds are infinity, negative and positive. Okay. In each case, the limit exists and is finite. If it exists and is finite, we say that the improper integral converges and that the limit is the value of the improper integral. If the limit fails to exist, we say that the improper integral diverges. Okay, so let's take a look at an example. So how do we set this up? Is the area under the curve of y equals ln x over x squared from x equal 1 to x equal infinity finite? If so, what is its value? So the way we do this, let's go back to the definition, is we start setting up the integrals as, you'll notice, limit functions. Okay, we take the limit as some variable approaches infinity. Okay, so we could do a similar thing here with this problem. So we would have integral from, and this would be from 1 to b, right? So we would say integral and it's going towards infinity. So we would say integral from 1 to infinity of ln x over x squared dx. And then we would convert this to a limit. So we would introduce a variable b as b approaches infinity. Of the integral of 1 to b of ln x over x squared dx. So now normally what we do is we integrate like normal, right? So we try to integrate ln of x over x squared. So we would do this with a integration by parts model, right? We could say that u would equal ln x dv, dv would equal dx over x squared so if that's the case, we have u equals ln x, that means du will equal 1 over x dx, and then v, if we integrate this, v would equal negative 1 over x. Okay, so when we go to integrate, we would have uv, so we have negative, that would be ln x times negative 1 over x minus integral uv minus integral of v du. So negative 1 over x times 1 over x dx. Okay, so this gives us negative ln x over x, and then here this would give us what we have, plus integral of 1 over x squared, right? We could pull out the negative and that'll affect that minus to make it a plus. So we get negative ln x over x, and then when we integrate this, minus 1 over x. Okay, so now the bounds were 1 to b, so we would put in b to 1. So keep in mind we have this limit. So now evaluate like normal, plug in the b, so we have negative ln b over b minus 1 over b minus, and then we have negative ln 1 over 1 minus 1 over 1. Okay, so now what happens as we go, b goes to infinity? Well, as b goes to infinity, this term goes to 0, right? 1 over something really big, that approaches 0. ln of 1 is 0, so this is a 0. Now inside here we have this minus 1, so if we have minus of a minus 1, we get a plus 1 there. And then the only thing left is here, this negative ln b over b. Now if we take the limit as b approaches infinity, we could divide top and bottom by, well, better yet, we could just do a L'Hopital's rule there, right? We could say negative, this would be 1 over b over 1. And so as limit b approaches infinity, that would make this top part become 0, right? Because b is getting really big. Numerator becomes 0. So this is 0 then. And then we have 0 plus 1. So we end up with 1. So therefore the improper integral converges and the area has a finite value of 1. Okay. Let's take a look at our next example. Okay, so this is the one where we have infinity at both ends, so we will have to split this one up. What we will do is set it up as the sum of two integrals, right? So we would do like negative infinity to 0 of dx over 1 plus x squared plus 0 to infinity of dx over 1 plus x squared. Okay, so we do it twice. Okay, so let's do the first part. So the way we'll set it up, we'll say limit. I'll introduce A. A is approaching negative infinity. And so this will go from A to 0 of dx over 1 plus x squared. Now, if we recognize this integral, this looks just like our arctangent, right, or inverse tangent. So we would have the limit as a approaches negative infinity. We could integrate it now. This will be inverse tangent of x and so that means we have the limit as a approaches negative infinity, inverse tangent of 0 minus inverse tangent of a. Okay, so that means if we do inverse tangent of 0, we get 0 minus. Now, inverse tangent of negative infinity. Okay, well that's going to give us negative pi over 2. Alright, so you want to think which of the angles is going to go towards negative infinity. So tangent would be sine over cosine. Right, and then we have the negative pi over 2. That would go towards negative infinity. Right, so this is going to end up giving us negative pi over 2. And then 0 minus negative pi over 2 would be pi over 2. Okay, now let's finish off the second part. So, same kind of style. I'll introduce the variable b. Limit as b approaches infinity. Integral 0 to b dx over 1 plus x squared. Okay, so we have limit as b approaches infinity. Again, this is an arctangent, inverse tangent, b to 0. So we have limit, b approaches infinity, inverse tangent of b minus inverse tangent of 0. Okay, inverse tangent of infinity. What goes to infinity? That would be the pi over 2. Right? So that would be pi over 2 minus inverse tangent of 0 is 0. And so we end up with pi over 2. Take the two areas, add them together. pi over 2 plus pi over 2, and that just ends up with giving us pi. Okay. Let's take a look at our next example. The integral 1 to infinity of dx over x to the p. So the function 1 over x is considered to be the boundary between a convergent and divergent improper integral. Okay, as long as it's in this form, 1 over x to some power, that's the 1 over x is the boundary. Improper integral converges if p is greater than 1 and diverges if p is less than or equal to 1. Example 3. For what values of p does the integral converge? When the integral does converge, what is its value? Okay. So let's set up our integral here. So we would set up, and we would do limit introduce the variable. Let's do b. B approaches infinity of the integral from 1 to b of dx over x to the p. Now another way we could rewrite this integral, let's just do the integral for now. This will be x to the negative p dx. Okay, so we could easily integrate this if we add 1 to the exponent and then divide by that power. Right, so this would typically give us, when we integrate here, this will be negative p plus 1 over negative p plus 1. And then we would go b to 1, and we would still do the limit as b approaches infinity. Okay. Now this divided by negative p plus 1, we could write that as a coefficient. I could pull it out as like 1 over negative p plus 1. We could just do this. We could say 1 minus p. Okay, so now we could evaluate. So we have 1 over 1 minus p, plug in the b for x. This will be b to the negative p plus 1. Minus 1 to the negative p plus 1. Okay, so next, now notice here the 1 to the negative p plus 1. This is important to know because some people, 1 to any power, right, is going to give us 1, right, because 1 times 1 times 1. So we can just simplify that part and leave it as a 1. So we have 1 over 1 minus p and then this will be b to negative p plus 1 minus 1. Okay, so when we take the limit as b approaches infinity, so if we have infinity here, now we could write this, let's write it in a little bit different way so we can see it more clearly. Now b is to a negative power, so I'm going to put that as 1 over b. Now if I pull out the negative 1, if I factor a negative 1, that's p minus 1. Right, so that would be p minus 1 as my exponent. So now as b is going to infinity, limit as b is going to infinity, right, so we're plugging in for there. If we end up with p becoming really big, right, then we would have a fraction of just 1 over p minus 1. Because what happens, this goes to 0, right? So think about this. If p is greater than 1, that means we would have the infinity here, and you would have greater than 1, so let's say 2, right, 3, you have 1 over infinity to the first, or infinity to the second. That's a really big denominator. That means this goes to 0, and then we have 0 minus 1, so negative 1, so we have 1 over 1 minus p times negative 1, which we could just rewrite and say this is 1 over p minus 1. Okay, so that's what happens if p is greater than 1. Okay, so it would converge to this scenario. And then if p is less than 1, think about that part, we end up with, let's say p is 0 here, we would get infinity to the negative 1. But now if you have infinity to the negative 1 in your denominator, that's really like saying you have infinity. And then you got to subtract the 1, which is still pretty big. Right? So that means if p is less than 1, which is how we thought about this, like we said p is 0. If p is less than 1, that means this becomes infinity. Okay, so So we would say that the integral we have converges to 1 over p minus 1 if p is greater than 1, and then it would diverge if p is less than 1. Let's just explore what happens if p equals 1. Alright, so p equals 1, we have the integral this would be dx over x. So that means we would take limit as b approaches infinity of 1 to b dx over x, which means we could integrate this. This would give us ln x. Okay, so this would be the limit as b approaches infinity, and we have ln b minus ln 1. Okay, so if we do limit as b approaches infinity, ln of infinity would be infinity and minus 0. So this will just give us infinity. Okay, so we see that when p equals 1, it also diverges. Okay, and this is important because this will come up later on when we have a series of this form, dx over x to the p. Okay, let's take a look at another example. What happens here? We have integral from a to 1 of dx over square root of x. So think about this. Now, this function, this is the function 1 over square root of x dx. If you were to do the graph of this function, this would have a vertical asymptote, right? And the graph would look it would approach the vertical asymptote. It would look something like this. Okay, so what we'll do is we'll cap it at 1. Right, because we're going from a to 1. Now, as we get closer and closer to the vertical asymptote, we're going to approach a from, we're going to go to 0 from the plus side, right? So what we would do is this, we would say limit a approaches 0 from the right, and then we would go a to 1 of dx over square root of x. Okay, so let's integrate this function then. So again, looking back at our function 1 over square root of x, this is the same as x to the negative 1/2. When we integrate that, that would be x to the 1/2 divided by 1/2. Divided by 1/2 is the same as multiplying by 2. So we end up with 2 square root of x, 1 to a, and then we still got limit as a approaches 0 from the right. Okay, so let's plug in. That means we have 2 square root of 1 minus 2 square root of a, limit as a approaches 0 from the right. So that becomes 2 minus. So if we go towards 0, right, and the square root of a, that goes to 0, right? Square root of 0.5, square root of 0.2, 0.1, square root of 0.01, right? This gets closer and closer to 0. So we just end up with the area to be finite value of 2. Okay, so that'll be part 1. We'll continue part 2 with our second video. Okay, we'll see you soon.